Hello everybody, welcome back to Science Academy. So in today's topic we'll discuss orbital magnetic dipole moments and Bohr magneton. Okay, so we'll start from the electron. Okay, the basic concept is that when an electron revolves around its orbit. Okay, so here now an electron revolving in an orbit about the nucleus of an atom is a minute current loop and produces a magnetic field. So we know that when an electron is moves like a loop. Okay, when an electron is moves around orbit like this, it means there is a current loop. Okay, because we know that flowing of charge creates current, and this constitutes a current loop. So from the plus 2 definition we know that when there is a current loop there is a magnetic field also. Okay, and magnetic field is correspond with the magnetic dipole. Okay, so electron is revolving like a current loop, there is a magnetic dipole north and south. Okay, so here we will compute the magnetic moment of this electron. So let us consider an electron of mass m and charge is E with a negative sign, because electron has the negative charges, moving with velocity of magnitude v in a circular Bohr's orbit of radius r. So there is a Bohr's orbit of radius r, the electron is moving like this with velocity v. Clear? So here electron is moving, there is a current produced, and the magnitude of this current is given by I equals to E divided by T. So where T is the orbital period of the electron and T equals to 2 pi r divided by v. So how this? Because we know that time period equals to total distance covered divided by the velocity. Okay, so here the electron covers the distance like the circumference of the circle. Okay, so circumference means 2 pi r with radius r. So 2 pi r divided by the velocity of the electron given is v. So T equals to 2 pi r by v. This is the time period. So putting this value in this equation, we will get I equals to EV divided by 2 pi r. Clear? Now from the electromagnetic theory we know that the magnitude of magnetic dipole moment, okay, orbital magnetic dipole moment, and we'll denote this by the symbol mu l with a vector sign. So mu l for a current I in a loop of area A is given by mu l equals to I multiply A. Okay, so I is the charge, A is the area of that loop. So its direction is perpendicular to the plane of the orbit. Okay, so understand this. Now substituting the value of I and A in this equation. Okay, I equals to this and A equals to pi r square. Okay, with radius r. So mu l we will get that EB divided by 2 pi r multiply pi r square, and the result will be EBR upon 2. Okay, so this is the orbital magnetic moment, orbital magnetic dipole moment. Now because electron has a negative charge, this dipole moment mu l is opposite in the direction to its orbital angular momentum L. Clearly, that is, you know that electron has the negative charge. Okay, so dipole moments. Okay, so this is very important. The dipole moment of electron is always opposite to the orbital angular momentum L, and from the Bohr's theory, okay, we know that the L equals to mvr. This is equation 1 and this is equation 2, and dividing these both two equations, that is mu l upon L equals to E by 2m. So mu l upon L, we get that this is the ratio of the magnitude of mu l of the orbital magnetic dipole moment to the magnitude of L of the orbital angular momentum. Clearly, again the ratio of the magnitude of mu l of the orbital magnetic dipole moment. Okay, this is orbital magnetic dipole moment mu l, and divided by to the magnitude L of the orbital angular momentum. So this ratio is given by E by 2m, and for an electron this is a constant. Okay, so this is independent of the detail of the orbits, and this constant is called gyromagnetic ratio of the electron. So mu L upon L is called gyromagnetic ratio. Now the above equation can be also rearranged to this form, like mu L equals to minus E by 2 multiply L vector. Okay, and mu L by L is called gyromagnetic ratio. So here the minus sign means that mu L is in the opposite direction to L. Okay, so I have explained this, that is the orbital magnetic moment is always opposite to the orbital angular momentum L. Now the unit, what is the unit? The unit of the magnetic dipole moment is ampere per meter square. Clear? So sorry, ampere multiply meter square or joule per Tesla, because joule is the unit of energy and Tesla is the unit of magnetic field. Now it is usual to write the last relation as mu L equals to minus GL E by 2m multiply L. So comparing these two equations, okay, we get that GL equals to 1. So GL is called the orbital G factor. It is very very important. GL is called orbital G factor. So the question is why we have multiplied this G. So we have introduced here to preserve the symmetry with further equation involving the G factor, which are different from 1, because in the other equations the value of G may be 1, 2. Okay, it depends upon the situation. So this is called the orbital angular magnetic moments. Now we'll move towards the Bohr magneton. So Bohr magneton, we know that from the quantum mechanics, the permitted scalar values of orbital angular momentum L. So the orbital angular momentum L, as per quantum mechanics, can be written as L multiply L plus 1 square root over h cross or h by 2 pi. Okay, so here L is called orbital quantum number. This is one of the quantum number. Now the mu L can be written as mu L equals to L multiply L plus 1 square root Es by 4 pi m. This is called orbital magnetic moment mu L. Okay, so now when we look up at this quantity, okay, Eh 4 pi m, this is all constant value. Okay, so we'll take this as a unit. So this is a natural unit and this is called Bohr magneton, and Bohr magneton equals to mu b Eh divided by 4 pi m, and putting all this value we will get that it is the value. So now putting the value of E, that is charge of electron, 1.6 multiplied into minus 19 coulomb, and H is the Planck's constant, and 4 pi m, m is the mass of the electron. Clear? So we'll get the value 9.27 multiplied 10 to the power minus 24 ampere meter square. So ampere meter square is the unit of also Bohr magneton mu b. So putting this value, so mu L in terms of mu b, okay, can be written as like this. So mu L equals to square root of L into L plus 1 multiply mu b. Okay, and this is the final equation. So this is all about the orbital magnetic dipole moment. Okay, so if you like this video, then please share and subscribe. Thank you.